All right, session is recording. There was no lecture yesterday. Lecture was a public holiday. All right, so no, there was no lecture yesterday. There shouldn't have been any academic activities in the university, what with it being a public holiday. You can do practical 2 with the knowledge you already have. I think so. We can just check that quickly. I see that the chat is on today. I think Dr. DeToy adjusted some of the settings because I see these are now recurring sessions rather than once-off sessions, and I think those default to chat on. Let's leave the chat on. If people start to abuse it, then we'll turn it off otherwise. Okay, anyway, so we'll be moving through the content. We'll discuss the practical 2 knowledge in the tutorial rather. So we'll move on with the theory here. Definitely by the end of the tutorial today, you'll have everything for practical 2. I'm pretty sure you actually do have everything for practical 2. That was one of the things that we were looking at. Certainly. So, okay, this clearly demonstrates a lack of. So the tutorials are typically ahead of the lectures. The tutorials cover the stuff that you need for the following week's practical. So the stuff that we're doing in today's tutorial is the stuff that you'll need for the practical you get on Friday for the following Friday. Obviously, because they started you guys so late, there's a little bit of a lag between the two, but we're trying to catch that up as quickly as possible. But no, you don't learn stuff in the class for that day's tutorial. That's definitely not how it works. The classes are typically more detail that cover the stuff that you've already seen in the previous week's tutorial. So you'll see the content of today's class will be more detail about the stuff that you saw for last week's tutorial. But also, since you've already done it in a tutorial, there's no it should be very familiar to you. It shouldn't be alien to you, maybe just different variations of what you've already seen. All right, so I'm going to share the screen now. And we'll move through the thing. I'll periodically check the comments, but as you can see, there is quite a lot to go through. So we will move fairly quickly through it. But as I say, a lot of it you will have seen already. So this first bit is just a general stuff on what programming languages are, which we've already mentioned verbally while discussing things like the numeracy in terms of high-level versions of the numbers that represent instructions that the computers can actually understand. So this is also just background stuff. All of this stuff could show up in the first semester test, but not in the second semester test or the exam, which are both very practical. So this is just pure theory, this first section of these slides. So let's move forward. And so as you can see, a computer is just a piece of hardware. It's a piece of general purpose calculating hardware. So without instructions for it to follow, which is namely the software, the computer doesn't do anything useful. Software is developed using programming languages, which can be at a variety of different levels of abstraction. They can be low-level programming languages, which is something like assembly language, which is basically just one step above the actual numbers that the machine interprets as instructions and data. One tiny step, barely a step, a small hop. Maybe later on we can go through an example of building our own simple assembly language, but with the shortened time that we have, it might not be possible. It's a nice example to do once we've done arrays later on, but we'll see. So C++ is a programming language, and it's a general purpose programming language. Some programming languages are specific for certain problem domains, certain industries, certain use cases. Others are meant for creating software that can be used in any context. And C++ is definitely one of those languages. You can write software for embedded devices, software for laptops, for PCs, software for servers. A lot of other programming languages are written in either C or C++ originally before they become able to host themselves. So that is C++. That's what programming languages are. C++ is very general purpose, can be used for a lot of things. There were a bunch of early calculating devices which became less specialized, more general as time went on. Abacus, the abacus is simply for basic arithmetic operations. Whereas if you move further to something like Jacquard's loom, it stored a pattern that could be replicated on fabric. So it's the first example of separating the operations from the hardware itself. The program for this loom in the 18th century was stored separately on punch cards to the loom itself. Then the first general purpose computing device was the Babbage's analytical engine, which he wasn't able to build. It was also in the 1900s, I think, but he was unable. Sorry, not the 1900s, as in the 20th century. Was in the 1800s, the 19th century, and it was built on mechanical principles, and he was unable to build it due to limitations in the machine tools available at the time, and I suppose various other factors. He technically could have built it. It wasn't beyond the realm of technology, but he fully designed it, and he did build a simpler machine known as the difference engine, which wasn't quite able to compute anything, but was certainly much more general than the computers that went before it. And it was successfully built later in the 20th century and worked flawlessly. And all the programs that were written for it by Augusta Ada Byron, the daughter of Lord Byron, also known as Lady Lovelace, worked perfectly. So the first programmer for the first computer was a woman. So it's interesting to note. And then Herman Hollerith's statistical tabulating machine, which eventually went on to become IBM. So all of that stuff is interesting background, but not super important. So we'll move through it and focus on the key take-homes. Computers made up of hardware. Computer systems are made up of hardware and software. The hardware is typically unchanging, and the software is changing. So your job as computer programmers is to write the software, as in to give precise instructions to the computer about how to achieve certain outcomes that it can blindly follow. You can think of a computer as being a very, 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 very fast idiot. So it's able to think creatively or understand things, but it can do very simple tasks very, very quickly. So if you, a human being, can give it precise instructions to follow, it can then do those tasks much faster than any human could do. And basically one of the tasks that we like to do is to write software for programs. So over the years, we've got better at writing those languages, and they've gotten easier to use, so that we need to specify less and less of the precise details for the hardware to follow. You'll never reach a situation where you don't have to fully clarify your ideas. So the actual task of a programmer is unlikely to disappear. It's simply, it might change form. We don't write in assembly language anymore. We now write in much higher level programming languages, but nothing takes away your responsibility of having to fully clarify your thoughts and ideas and fully understand the business process or logical process that you're trying to capture in code. So computers are made up of hardware, like a central processing unit, that basically performs the arithmetic operations very quickly. I'm going to quickly take a look at some of the comments that have been posted, but I can't answer every single question. Will you be tested on this? It can show up in your first semester test. So, all right. Yeah, no, as far as I can tell, our connectivity is fine. That should all be okay. We'll discuss the linkages between the computer and the RAM now. So yeah, we had the central processing unit. We need an area in which to store the software and the data upon which the software will operate. So that's stored in main memory, which is typically implemented using something called random access memory, which is basically silicon circuits that store electrical charges at fixed locations. Those electrical charges represent either ones or zeros due to the amount of charge stored at each location. And those could be easily overwritten, but require a continuous amount of power to maintain that stored data. So if the power is disrupted, the values dissipate, and you can't access that anymore. Whereas secondary storage devices typically use something more permanent, either aluminium platters with DAS with magnetic data stored, which is obviously permanent, or semi-permanent. You can turn off the computer and then reboot it later and the data is still there, or sort of like the advanced descendant of a capacitor, which the flash devices use. The physics behind that is actually quite scary. So it's much more difficult than simply reading and writing magnetic values at particular locations. But the flash data doesn't require any moving parts, or flash storage doesn't require any moving parts, and does persist when power is lost. So it's typically become much more common now. And then things to get data into and out of the computer system, which we refer to as input and output devices. So here are the linkages in general, the broad idea of what the computer architecture looks like. And we call this the von Neumann architecture. We've got a central processing unit, which is linked to memory. These linkages are typically referred to as buses, linkages to input and output devices, and linkages to the secondary storage. This is very abstracted. This is a kind of design that you could apply to anything from a cell phone to a smartwatch to a CPU, to a laptop, to a desktop, to a supercomputer. Will follow some variant of this design. So all of our modern computer systems represent data in some version of this von Neumann architecture. Main memory itself, you can think of as a sequence of locations, and in those locations, numbers can be stored. We will discuss this idea in much more detail when we take a look at pointers and direct memory management in C++. It'll become much more important. But you can think of it as a linear sequence of addresses. These are these numbers going up sequentially, 1000, 1001, 2000, 2001. And each of those numbers represent a location where a different value can be stored and read later. So we've mentioned that there's a linkage between the RAM and the CPU. Programs get stored in the memory, and your program is simply a sequence of numbers in memory, and those numbers get interpreted as instructions that operate on other numbers also located in memory, and later on in secondary storage. But for stuff to actually be operated on, it needs to be read from secondary storage and stored in memory, and the CPU actually operates on it in memory. So as I said, that memory is what we call volatile. When the power is lost, the values become indistinct and unrecoverable, and the data is lost. There are other kinds of memory that do exist, like bubble memory, and some more sophisticated descendants of it, which can persist even the RAM when the power is lost. But the thing is, we're actually so used to being able to reboot a computer to reset things that I'm not sure that it's such a great idea that everything should be persistent, because the clean slate you get when you reset a computer is often kind of built into people's expectations about how you might be able to solve a problem. Many times you're told to reset the computer, and the reason for that is to clear the memory and load everything from scratch. So that there is persistent primary memory, but I don't think it'll replace the volatile memory that we have entirely. So as I said, it's a sequence of locations called memory cells. Each memory cell has an address, basically a number that you can use to access it, and it stores a value, which can be either interpreted as an instruction or as data. There's no fundamental difference between a number that represents data and a number that represents an instruction. And in fact, the way that malware, such as viruses and worms and other kinds of dubious software work, is they trick your computer into treating data, i.e. the virus that gets loaded into memory, as instructions, and to begin executing that. So this lack of separation between instructions and data is incredibly powerful, because it lets us have this very flexible design that can represent any program that can be designed and then executed without changing the hardware at all. But the consequences, of course, that anything can be loaded into memory and executed with enough knowledge, and that includes stuff that you don't want running, like viruses and worms and so on. Secondary storage, as you said, hard drives of various forms, flash drives, optical drives, CD-ROMs, DVDs, Blu-rays. Not that these are so common anymore, but they do still exist. Input devices, for us, we'll mostly be focusing on the terminal, which basically receives its input via the keyboard, and the output as well will be displayed to the screen, monitor. However, if you're doing informatics or if you go further in computer science, do graphical user interfaces, which make use of the mouse as well as other things, potentially cameras and other things, and other secondary storage devices. So when you're loading data from the hard drive into memory, you can treat the hard drive as being an input device from that point of view. So even though the user is not typing anything in, data is flowing from outside the program or outside the environment into the environment. All right, so that's that. Software itself. Software is written to perform certain tasks and operates at different levels. You've got systems programs which control the computer itself, such as the operating system, which there's many tasks involved there, which you'll learn all about in your third year when you do operating systems. But managing the memory, managing input-output devices, managing the format of secondary storage devices. And then at the higher level, the level which you'll be programming at, will be individual applications that perform tasks such as word processors, spreadsheets, games, the stuff that users will actually interact with. These application programs interact with the system software, and the system software interacts with the hardware. So this operating system forms a sort of glue, a sort of bridge that links the programs that most programmers write to the hardware. And that means that the programmers don't have all of the details about the hardware. They just need to know the details of the operating system, which might be running on different kinds of hardware. Most of the time, the programmers don't care about that, which is good. Computers understand various kinds of signals. You get analog signals where you've got a continuous value that varies. So continuous is in non-discrete. So it can take in infinite number of values between any 2 points. And those typically take the form of waves, normally sine waves. So when data was sent over the plain old telephone system via modems, that was by modulating a continuous analog signal. Computers these days will internally typically represent data digitally, so sequences of ones and zeros. And those ones and zeros represent numbers, some of which correspond to a list of instructions the computer can understand. That's known as the instruction set for the computer. And so numbers that are able to be interpreted as instructions for the computer form the machine language of the computer. We've seen bits and binary digits and binary codes and so on, so we don't need to go into too much detail. During the tutorial, we took a look at the ASCII table, and you can see one of the VPL exercises deals with that. So basically the way in which a number can be used to represent a character by being a lookup value on a table. You can see those sort of things. So 128 characters, the value A, that's the 66th character, but obviously you want to see that number in binary, is what the computer will represent it as, and so on and so forth. And we've seen that we use base 10, but computers use base 2 last week, and we saw what that means. And various sizes involved with groups of bytes. So a byte is typically 8 bits, as we saw, a group of 1,024 of them. So not 1,000 of them, 1,024, because that's a base 2 kilo, not a base 10 kilo. Technically, they refer to these also as kibi bytes because it's a kilo binary byte, not a base 10 byte. So if you ever buy from Vodacom or MTN or whatever a gigabyte of data and you get 1,000, or sorry, you get only what's it, a million bytes or whatever, then you know you've been cheated out of this remainder here, because technically they gave you a base 10 giga, not a base 2 giga. So you can bring them up for false advertising, and those numbers go up. At the moment, we're sort of operating in the terabyte level for users and these other more exotic extensions in the big data space on cloud and server operations. So as we've seen, the machine language typically takes the form of numbers, but these numbers often split into 2 sections. The one section represents, or 2 numbers separately, if you want to think of it like that. The first number is called the opcode, and the second number is called the operand. The opcode represents the actual instruction, and the operand represents the data upon which the instruction is being applied. So in this made-up machine language, that number represents load, that number represents multiply, that number represents store, as in take the value from the CPU and send it somewhere in memory. And these represent the either the places in memory where the data can be found or the data itself, depending on how that particular machine language works. So obviously this is impossible, not impossible, but really difficult for programmers to work with. So the next level above a machine language is an assembly language, which basically just replaces these difficult to remember numbers with textual representations. So a named location called rates, hours, wages, and a fixed instruction name, load, multiply, store. So you don't have to remember those binary numbers. So the difference between a machine language and an assembly language is actually very small. It's in fact not really a compiler per such. It's more like just a translator, which is the correct term for it, because it simply maps these things onto those things. The actual language at this level is no more expressive than the language at the level of the machine code. It's just easier for a human to read and write. So whereas something like this is much more expressive because we're combining several operations into one instruction. We're saying take the value at rates, multiply it by the value at hours, then store that same result inside wages. And you can see that actually one statement in a higher level programming language can boil down to 3 or 4 or even many more statements in the lower level machine language. And that's typically what happens. The higher you go in terms of the level of the programming language, the shorter the instructions are, and the more that they actually mean in any one particular instruction. But at the end of the day, a compiler will take this high level instruction and turn it into a low level, well, machine code instruction equivalent. So every one statement in your C++ code doesn't mean it's one instruction for the computer. It could be, and often is, several instructions. So high-level languages, things like Fortran, which is still used, COBOL, which still exists, which is the common business-oriented language, but I don't think anyone's been starting new projects in COBOL since the 90s or maybe even before then. But if you're a COBOL programmer, you made a lot of money during the late 90s updating software for the year 2000. C, a very low-level language, but it gave birth to C++, and C# is a language that looks a lot like C++ and C, but is actually more similar to another language called Java, which you will learn. And then very ultra-high-level programming languages like Python, which almost read like executable pseudocode, but are very slow, because every instruction in Python needs to be translated into quite a lot of instructions in in machine code, and it actually does that through several steps. So they're actually typically much slower, but often that's not a big deal. C++, on the other hand, is interesting because you can write very low-level code that's very fast, as well as very high-level code that also tries to be as fast as possible. So it's a difficult language, but it's a very quick language if you know what you do, or the programs run very quickly if you know what you're doing. So the piece of software whose job it is to translate the program in a high-level language into the lower-level language is called a compiler. And for example, a bunch of instruction will be translated into this. But obviously this by itself is meaningless. It needs all of the stuff to talk to the operating system and to understand what input and output is, and to be basically put into a context. So as you can see, the C++ version of that would need a main and all of those other things. So this C++ program is basically just a hello world equivalent and simply outputs value to the standard output stream, as we've discussed. All right, so your job as a programmer is to basically do this. You write code in the text editor, link in other libraries that you need. The compiler compiles your code, brings in the compiled code from the library. The loader joins everything together in memory, and then the program starts running, and it starts running at main. Main is the entry point to all C++ programs. It's the first set of instructions that gets executed, will be the ones that are found in main. IDE, glorified text editors that make that easier. Sorry, I'm just checking. I got a notification, but I'm not quite sure what that was. Maybe that's the timer warning. I do want to at least finish this set of code before, of slides before we end. Not all all of them, but up to the next section. So as you've seen with code blocks, that allows you to edit the code easily, and you just click a single button to compile, and it gives you errors and things like that. So this is a workflow for the process run by the programmer. They write a program in an editor, the preprocessor brings in the libraries, the compiler converts all of the code into source code. Pre-compiled libraries, like the standard libraries, get brought in by the linker, loaded, brings everything into memory, then it gets executed. Your job as the programmer is something more like this. You must understand the problem, analyze it into a series of steps, turn those series of steps into an algorithm, convert that into C++, then the preprocessor kicks in, all of those other steps join in, and at any of these points errors can occur, in which case you must either rethink your code, rethink your algorithm, or rethink your understanding of the problem. So these are important flows of thought that you as a programmer need to follow. So this is the basic process for understanding a problem. What steps do you need to understand? So it's basically what I've said before. Once you've created the algorithm, so remember the algorithm is the series of steps that the computer must follow to transform your input into the desired output. And if it does that correctly, you can verify that for any given input, the correct outputs are occurring. You can see that on the VPL, when you click the test button, that it sends a whole bunch of test input to your program and checks to see if it gets the correct output that it expects. So yeah, so that basically just in text what I've said in memory. There's no guarantee that your programs will run correctly. The compiler will just check that your program follows the rules of the language. You could still have understood the problem incorrectly. So just because your program compiles, that doesn't mean that you're getting good marks. You've written a program that exists, and a program that's correct syntactically. All right, let me just quickly finish this off. So there's two main programming methodologies that exist. Not two main, there's two that you typically start with. Structured programming, which is built around functions and procedures and so on. And that's what we do in Computer Science 1A. And then the next important one is object-oriented programming, which we'll do in Computer Science 1B. So we'll discuss all of those in details going forward. We've mentioned that C++ is standardized in a standard known as the ANSI standard. Also the ISO standards, they're joined, American National Standards Institute and International Standards Organization, and we use C++ in that way through the compiler, which follows that standard. I'll see if there's enough time to answer some questions before the time runs out. I just want to quickly give you your code. For late viewing, for those people who need to view things late. So I'm just going to quickly see now if there are any questions I can understand. 15 minutes. I'm getting noises from the system, and it's not just messages coming through. I wonder what it is. Oh, well, that's great. If I still have some time, then that's wonderful. Yeah, no, that's fine. The system is making weird noises at me. Where do you send the code? This should be well established by now. Oh, it's people raising their hands. Okay, yes, please treat this like a live lecture, and I'll come back to this at times and answer the questions. The code is for late viewing. You should know this if you've been watching, if you've watched the lectures. Remember, all lectures are compulsory, so the ones that you've missed, you have to watch the recording of, and in the recording you get given a code, which is to show you that you've watched late. And so all of these things have been answered. If you've joined late, will you still be on the register? No, that's what the code is for. All right. Where do we send the code? Blah, blah, blah. Okay, so we still got plenty of time. I'm happy that you're getting things. Low-level languages are easily understood by the computer. High-level languages are easily understood by a programmer. That's perfectly correct. Absolutely spot on. Program and high-level language convert to a low-level. That's absolutely correct. So for what it's worth, this is an interesting statement. Any programming languages that's what we call Turing complete can implement any algorithm that can possibly exist. But it's not fun to do it in all of those languages. So, so technically anything that is capable of basic loops and basic storage of information can solve any problem that can be solved. But you want to do that. So low-level languages are closer to machine language. High-level languages are closer to human understanding. Not necessarily closer to English or natural language, but closer to some level of human thought, maybe closer to mathematics, maybe closer to, I can't move slowly. You guys started like weeks late. So we've got, in this set of slides alone, 115 slides. So it's your responsibility to go through the recordings. And if you then have any further questions, ask that in the Discord server going forward. I can't change the requirements for what you need to be assessed against because that's certified by the British Computer Society. So unfortunate. All right, so a bus is just a channel that links two portions of the computer, and data or power can flow along them. Is there a semester test? That's in the learning guide, but it's not far because next week is Informatics 1. I think we're the week after that. All of the stuff is recorded, and I think that's okay. So we can move forward from now. I just want to see if there's any new things. Okay, now the code is for people who are watching later. Discord server for week and still needs general. Okay, so just if DM me but do it during working hours. If you DM me during when you're connected, then I can add you. So because we only see the notifications that come in, we have to know to add you. So please just contact us or even email us while you're connected to the Discord server. Object-oriented programming, it's a way of grouping data and behavior together into a single unit. You'll do it in the second semester. And as I said, the stuff has to be assessed. You have plenty of time to go through this work later. All right. All right, so let us continue. So if we end it, we've got more than 10 minutes left. So let's continue. Right, and also remember all of this stuff is stuff we actually did speak about previously. So none of this is super new. It's just with pictures. All of these things were mentioned during the previous set of lectures last week when we spoke about binary representation and in the tutorials when we spoke about the ASCII table. None of it is super new. It's all just now you have slides that represent the data. All right, so now we're going to take a look at simple C++ expressions. All of this stuff was covered in last week's tutorials. So again, shouldn't be super new. You must keep up to date with the tutorials that have passed. So this will be basic input and output and arithmetic expressions and basic data types that exist. So let's take a look. So you said a computer program, sequence of statements, whose objective is to accomplish a task, typically written in a higher level programming language. And programming is the process of converting the written instructions into a sequence of steps and implementing them in a programming language that a compiler can understand. So if you think of it like a recipe for a particular dish that you want to prepare, you need to follow the steps in the right order, with the right amounts, with the right temperatures. Otherwise, your end result is not going to be what you expect, even if the inputs were correct. So here's a simple program that calculates various attributes of a rectangle. So we can see here the basic building blocks of a program. We can see there's a comment at the top, which is for the human to read. Here is a preprocessor directive, which brings in the input-output stream library. Here is namespace usage, which brings in all of the names in the standard namespace into this program so that you don't have to fully qualify the names of C in and C out in the various input and output streams and end line and so on. This declares a bunch of variables of type double, which stores real numbers. This sends output to the output stream. This IO manipulator here represents the end of the line and flushes the, which you don't really have to worry too much about, so you can just think of it as representing the end of the line. These are assignment statements, which store values inside those variables. This is an arithmetic expression, which performs a calculation. The value inside length gets added to the value inside width first because of the brackets, and then multiplied by 2. And this as well, the value that's stored inside length gets multiplied by the value that's inside width and stored inside area. These statements here simply output the string length equals to, width equals to, perimeter equals, and area equals to, followed by the values stored inside those locations. So if we take a look at that in more depth, this is basically what I said. Variable declarations of type double, we use those for real numbers. And basically all of the things that I just said previously but pointing to those particular locations. All right, so that's stuff that we covered early last week in the tutorials. So remember, you can think of the identifiers, these variables, as being places in memory with a name. You don't have to worry about where they're stored in memory. All you need to know is their name. And when a value gets assigned to it, that value gets stored inside that location, referred to by that identifier. So when I say length in the code here, it will retrieve the value that's currently stored there. In that case, 6, and so on and so forth. So a basic C++ program will be made up of multiple components. It will be made up of sets of subroutines, sometimes called subprograms, but in C++ we call them functions, like in maths, which then basically group related operations together in a way that can be reused. They can be written by the programmer, or they can come with the standard library, or they can come in predefined external libraries. The rules for what makes a correct C++ program are called the syntax rules. So if you don't follow those rules, the thing you've written isn't a C++ program, and the compiler can't turn it into a sequence of machine code instructions. However, just because your program follows the syntax of the language, it doesn't mean that it's semantically correct. The word semantic means meaning. So basically the semantic rules are how closely the code you've written follows the actual problem description you were given. And the programming language itself is a set of these semantic rules, these syntactic rules, as well as, you got two levels of semantic correctness really. How well you've implemented the program, and then within the programming language, there's a bunch of rules related to meaning that you can't really see from the syntax. For example, I could create a variable called width, but I could have declared it as a textual variable, a string, and then tried to store a number inside it. Then the compiler would yell at you. But that's based on this line over here where we declared it. If we declared it as something else, if we declared it correctly, this line would be correct. So just looking at this one line, it's syntactically correct, but its semantic correctness depends on whether or not this statement here agrees with the type that we're storing in it over here. Right, comments, as I said, they're for the user to read. They don't actually get interpreted by the compiler at all. In fact, the compiler strips them out before it sends it to the screen. The preprocessor strips it out before it gets to the compiler. And you can represent a single line with a double // and then anything that you say on that line gets ignored. Or if you want to group multiple lines together, you say /*, and you end it off with a */. Then as everything between those two symbols, those two tokens, will be ignored. There are a bunch of special symbols that have meaning. We'll encounter them as we go forward, but the basic arithmetic operators, things like semicolons for ending off a line, these all have special meaning in C++, which we'll unpack going forward. You've already seen the arithmetic operators and the semicolons, and you've seen, for example, the stream insertion operators being used to send values into the output stream. So there are also special reserved words that you can't use to make variable names or later on function names. They have special meanings that can't be changed. For example, the different data types that we use are reserved words or keywords. So int, float, double, char, const, void, return. You couldn't create a variable with that name. Even though technically speaking, it follows the naming rules that are legal for variable name. You're not allowed to use them. They're predefined. Whereas an identifier is something that you, the programmer, have created. For example, a variable. It can be made up of letters, digits, and underscores, but must always begin with either a letter or an underscore. And we, in our programming style, as you've seen in the previous weeks, start them off with a short sequence of letters that represent the type. For example, int followed by the name of the variable. So, for example, int total. C++ is case sensitive. So number in all caps is not the same as number in lowercase. That's very important because not all programming languages are case sensitive. Visual Basic that you do in informatics, for example, is technically not case sensitive. But the IDE is so sophisticated, it'll often just rewrite the things that you type the way you originally declared it. So it takes away that issue most of the time anyway. So two examples of predefined identifiers. They're not reserved words, but they come from the IOStream library, are cin and cout, the input and output streams that you've seen in that code. So you could create a variable called cout, but not if you've simultaneously brought in the IOStream library like so and used the standard namespace. Then you'll have a collision. So you can only have one identifier with the same name in a particular scope, we call it, in a particular region of the program where that name is valid. I'm going to take a look at some of the comments or questions. So it's not a rule, but it's the way in which we program. So it's our style. Does subroutine and function mean the same thing? The word subroutine in C++ has no meaning. Subroutine is a general term to refer to how you break a program up. In C++, there's only the term functions. Okay, we'll discuss float and double in these slides, but basically a double is more accurate than a float and can store a larger range of numbers. We will only use double. Please, you join today's TUT if it's convenient for you. You can watch all of the tutorials if you want. There's no reason to only watch one tutorial or to watch the one that happens to be on the timetable. So don't worry about SI units at the moment. The output will sometimes show SI units, but in your code you can, and that will be discussed, but don't worry about it, don't bother. So only functions. Test one is only theory. Yes, we discussed that. There's a lot of evidence that people have not been attending the previous lectures. They're all compulsory. So programming and coding are typically the same thing, although coding is often seen a bit more simplistically as just the act of translating the requirements into source code, whereas programming is sometimes considered more generally involving some of the problem-solving aspect as well. Coding is a little derogative of programming is more general. All right, we're going to convert a Visual Studio solution. Nope, definitely not going to do that. Okay, and then we're back to where we were. No, you'll create as many variables as you need of whatever types you need to solve the problem that you're solving in. The link is on Eve to access Discord, and you don't want to use VB in place of code blocks for computer science because we use C++, not Visual Basic. Okay, we do code in the tutorials. Sometimes we'll do it in the lectures, but we'll focus more on code after the first semester test, which is theory in the source code. And then we'll talk about namespaces in more detail later on when we do libraries. If you do Visual Studio, that's on you. It's your responsibility to provide a practical that the assistants can mark. So you can write it in Visual Studio all you want, but you need to give them a CPP file so that they can just double click on your thing. It's not their job to restructure every project that they receive. So feel free to write it in C++, but you must convert it into something for submission. Source code refers to the text file that contains the programming language code inside it. Neither 03 or 01 are versions of code blocks, but I think if you've got 13 versus 20, then there's not much difference. I mean, there is a version 3 and a version 1, but those would have been many, many years ago. All right, let's continue. We don't have much time really, but let's continue until the thing yells at us. All right, so here's some examples of legal identifiers in C++. First, conversion, pay rate. Here's some examples of identifiers that aren't correct. You can't put a space in an identifier. You can't include an exclamation mark. You can't put a symbol like plus inside it. You can't start with a digit, although you can have digits later on. So you can see here is how we correct those identifiers to make them syntactically correct. Obviously, if they refer to variables, we would then also want to prefix them with the type of the variable if you're following the Hungarian notation style. If you're not, then that's not an issue. In addition to the characters you can see, there are also white spaces, such as tabs and blanks and new lines and so on. White spaces are used for formatting your code, but they don't have any deep meaning, apart from maybe causing issues if you put one inside an identifier name. However, we'll write code in a way that's typically easy to read. And by following the tutorials and by looking at how the code is laid out in the textbook, you will see what that style is. Okay, when we're talking about the values in C++, there are different types that those values can follow. And we'll look at the simple ones that come with C++ originally, and later on in the second semester, you'll create your own new data types from scratch. So even in this one, we'll create some composite data types. So you've got the simple data types, that basically things like integers and booleans and doubles and so on. Structured data types, which we will look at this semester, where we group sequences of related data together or groups of different data together into a single unit. And then pointers, which we will also look at in the semester, a pointer location in C++. All right, so if you look at simple data, there's three categories. There's integral data, which basically refers to numbers without a decimal. So all of these form integral data. Very importantly, and as we discussed in the tutorial last week, characters are simply numbers. So they count as integral data. Then floating point values, so that's decimal numbers, things that have a dot fraction. And then user-defined data types to represent separate values called enumerations, which we will look at in this semester. So sequences of related values, like error code. We could create a group of error codes for our program and store them in something called an enumeration. We will do that later on. Here's some examples of simple data types, integers, and the range of possible values they can take, and how much space in memory they are used. Now, this space in memory actually varies from compiler to compiler, so there's no point in memorizing that. It's not standard. But the range of values may be defined by the C++ standard. So, or for some others, it might not. But typically, these ones given here will all hold true. For what it's worth for Booleans, typically what happens is we simply store them as a number, and we check to see if that number is 0 or non-zero to represent either true or false. The integer data type, some examples of valid integer types. You can make them negative. You can specify that they're positive, although it doesn't actually change anything. And don't put commas in for long numbers, because commas don't meaning in that sense. You'll confuse the compiler. So it's not like when we write very long numbers and we put commas as a space separator, or even don't put spaces. Just write them as one long sequence of numbers for now. The Boolean data type represents truth or falsehood. So for logical expressions, we'll make a lot of use of it. And it's got two legal values that are keywords, true and false. All bool, true and false are all reserved words. Got the character data type. It's a tiny number. It's normally equivalent to the short data type, and it stores values that are represented as a single character within single quotes, including things like the blank space, which is an open space, close quote. We discussed in the tutorial last week that they actually represent numbers that show where in this table, the ASCII table, the corresponding glyph, as in the image of the what the character looks like, is stored. So if you sort things on the basis of their ordering according to the character set, that's called the collating sequence, and it correlates to lexicographic sorting. Actually, that's not quite true, because lexicographic would treat upper and lowercase things more similarly, whereas this, as you saw in the tutorial, the uppercase letters are far away from the lowercase letters in the ASCII table. You can, now there was a question earlier about writing long numbers in scientific notation. You can do that. There are some examples of that. Only do that if you're really sure you know what you're doing. And we typically won't be working with numbers that require such high precision that you'll need to write them out in floating point notation. But this is the representation for floating point notation. So rather than saying multiplied by 10 to the power of whatever, you say e and follow that e the exponent, so 1 or -1 or -5 or nothing or whatever. But we won't ever write any code nested that requires that. All right, I think that's a good point. It looks like the new configuration doesn't sound an alarm like the old one did. I think we've gone a minute over time now. Let's just check that. Yeah. Yeah, sorry, we've actually gone well into the 5 minutes afterwards and 1 minute into the tutorial. So I'll switch over to the tutorial now where we will work on code. So thank you very much and have a good evening, and see some of you in the tutorial now. I will switch over there momentarily. Yes, there's a tut now, and we're switching over to it now. Again, this has been said multiple times, code is being demonstrated in the tutorial.